Howdy, everybody. We're here for Advent of Code 2016, day 22. Hopefully, recording goes well. I've had problems a couple of days. Yeah, let's just keep pushing through it, I think, and then we're getting close to the end, and I may hop over to Everybody Codes for a little bit of time. We'll see. I also don't know when these videos come out, like the order, so it may be that you see this before or after we do some of the live solves for some of the puzzles coming up. So anyway, that's all to say. I plan to keep making videos. I'm having fun doing it. Hopefully you're having fun too. If you have any, anything you'd like to learn about or some puzzle you'd like me to try and solve, that would be great. My kids every once in a while, just the other day, came up and said, "Dad, I have this math puzzle," or whatever. It was one I'd seen before, so it wasn't hard to solve. But anyway, just something to think about. So let's just get started. Day 22, grid computing. You gain access to a massive storage cluster arranged in a grid. Each storage node is only connected to the 4 nodes directly adjacent to it. 3 if the node is on an edge. Connect to the 4 node, 3 if it's on an edge, 2 if it's on a corner. Okay. Got it. So it's like a rectangle or something like that, right? You can directly access data only on node X00, I guess is what that is, but you can perform some limited actions on all of the other nodes. You can get the disk usage of all the nodes. The result of doing this is your puzzle input. Is it actually a df command? Yeah, it looks like it. Okay. Whoa, that's a lot. Is it in order? Doesn't look like it's totally in order, but it looks there's a lot. Okay. You can instruct a node to move, not copy all of its data to an adjacent node. You can instruct a node to move all of its data to an adjacent node. If the destination node has enough space to receive the data, the sending node is left empty after this operation. Nodes are named by their position. The node named 1010 is adjacent to 910, 1110, 109, and 11 or 1011. Yeah, so like the cardinal directions. Before you begin, you need to understand the arrangement of data on these nodes. Even though you can only move data between directly connected nodes, you're going to need to rearrange a lot of the data to get access to the data you need. Therefore, you need to work out how you might be able to shift data around. To do this, you'd like to count the number of viable pairs of nodes. A viable pair is any 2 nodes, regardless of whether they are directly connected, such that node A is not empty, so it's used as not 0. A and B are not the same node, and the data on node A would fit on node B. How many viable pairs of nodes are there? Okay. I mean, if you're getting just, you want a total sum of all the viable pairs, that's just like the product of A and B, right? So we just had to parse the nodes. And then use this logic to determine which ones are viable and get a count. Okay. What did it look like? So we skipped the first 2. And then our lines look like this. We need used and available. I don't think we need the other ones, right? Size and use percentage. We can actually derive the other two if we need to, so we do only need used and available. Our struct node. Used, usize, available, usize. So we're just going to parse those, and then we need these rules right here. Okay, so I think we just split on white space. The first one, oh, how am I going to store these? I was thinking I want to use a hash map for the X and Y's. It looks like we're building a grid. I guess I don't know what part 2 does. We definitely don't need the grid in part 1. Sorry, I don't know which ones of these I'm going to use, so I'm just putting them all in. Yeah, if I store them as a hash map later, I may change that around, but we'll see. So let's parse so let name parts equal parts 0 dot split on dashes. Collect. So the X is going to be the name parts 1. Skip the first one. Dot parse And the Y is going to be this. Oh, so I can just kind of do this. So the used is, where did that go? I already forgot. It was these two, right? Used and avail. 0, 1, 2. What is it like? 19? Huh? Oh man, I was totally missing. Okay. So our input is going to be a vec of node. And then for our parse input, do node parse. That. Invalid digit. Parse int error. Invalid digit. This is where the unwrap would actually be helpful, right? 0, 1, 2, and 3. Trim the T's. Oh, I need to trim lines, skip to. There we go. So for part 1, I think it's just nodes dot, or sorry, input dot cart iter dot Cartesian product. So the rule are, oh, I guess they're called A and B. The rule is A dot use does not equal 0, and A does not equal B, and A dot used is less than B dot avail, right? Equal. Like that. 124 is a very specific number. Okay, but it is the right number. Okay, not too bad. Part 1 pretty easy. It was just, yeah, if you think about what it's asking you, is it's just saying how many of the product of A and B, how many of them match this criteria. So once you parse them, you can literally just use itertools to get the Cartesian product and then do your filter. Okay. Part 2. Now that you have a better understanding of the grid, it's time to get to work. Your goal is to gain access to the data, which begins in the node with y equals 0 and the highest x. That is the node in the top right corner. Okay. For example, suppose you have the following grid. Okay, so here's a smaller example. In this example, you have a storage grid 3 nodes wide and 3 nodes tall. The node you can access directly is at 0, 0, is almost full. The node containing the data you want to access, node x20, because it's y0 and the highest x value, contains 6 terabytes of data, enough to fit on your node. If only you could make enough space for it to move there. Fortunately, node x1, y1 looks like it has enough free space to enable you to move some of this data around. Okay, so yeah, this one's totally empty. Got it? In fact, it seems like all the nodes have enough space to hold any node's data, except XO at Y2, which is much larger to very full and not moving anytime soon. So initially, the grid's capacity and connections look like this. The node you can access directly is in parentheses. So this is the goal node. The data you want starts in the node marked in the square brackets. In this example, most of the nodes are interchangeable. They're full enough that no other node's data would fit, but small enough that their data could be moved around. Let's draw these nodes as dots. The exceptions are the empty node, which we'll draw as an underscore, and the very large, very full node, which we'll draw as a hash. Let's also draw the goal data as G, then it looks like this. This is substantially different than part 1. Okay. Okay, so we're translating this to this. The idea is here's the data we want. Here's where we want to put it. And we have a little free space thing. It's like one of those little slide puzzles almost. Is that what we're doing? The goal is to move the data in the top right G to the node in parentheses. It's definitely a simpler version though, because we don't have to get them in order. We just have to get one of them moved over. to do this, we can issue some commands to the grid and rearrange the data. Move data from node Y0 or 0, 1 to 1, 1. Okay. Now this one's empty. Now we can move the goal over, and that swaps it to here. And then go down, left, left, up, and then swap again. So after 7 steps, we've accessed the data we want. Unfortunately, each of these moves take time and we need to be efficient. What's the fewest number of steps required to move your goal data to the node 0, 0? Okay. It feels like a graph problem, especially when they're asking something fewest number of steps. I think we've said this before, that screams BFS. So there's 6 here, 7 here, 6, 8, 6, 7, 28, 8. Okay, so it does seem to say, and it said it somewhere here, right? Yeah, right here. We're basically just turning this into like a graph, I think. So I probably, I should have had the, made a hash map instead. I guess I'm just trying to determine how we would go about this. I may need to just draw our graph out. In this example, most of the nodes are interchangeable. They're full enough that no other node's data would fit, but small enough that their data could be moved around. Right? Like what that's saying is like there's some subset of these that are not walls and the rest are walls. I think that's essentially what we're trying to do here. But like how to determine that? I think you just use a neighbors function, right? Is you say, okay, if I know this one's the free one, so here's like quote unquote where I'm at, the free space. This one's a little silly because I think my goal is to get right here so I can move this over. We'll have to look at my map. But like the goal is to, I may have to do this recursively. We'll have to see. Let's think about it, but or iteratively over and over again. But like, I don't know. Say I'm right here and my goal is right here. I have to move 8 terabytes of data. So I just need to find my neighbors that are able to move 8. I'm able to do 8 terabytes of data to move to, right? Which is all of them. So I can move them all. I can move all of these. The one I can't move is like clearly right here. So if there was a bit like, imagine this big one is right here and I was right here and I need to get to right there. It'd be like, okay, I guess I go like this to get up to it or something along those lines, right? I mean, I suppose I could move this one. That actually makes it worse, I think. But okay, I want to draw mine out a little bit like this to start. So let's change our thing up a little bit. I'm not going to include the location, and instead we're going to do a fx hash map of point node. And so I'm going to return a point node. Like this. Oops. And then I just need to okay, well this will be an FX hash set. It's like key A value A and then KB value B. Um so it'd be ka.use does not equal this. Or no, the value ka or like that. Okay. So what I'm doing, since it's now, I realize it's a little obfuscated, but since it's now a hash map, this iter is going to return the key values as tuples. So we just do this. So we could call this like a why do I keep doing that? Node B. There you go. Okay. Do I know how big my grid is? I don't know. So let min a or min x equal input dot iter dot max by key. Or can I just do keys dot max by key? Or I can just do map p dot x dot max. Oh, this one's a dot unwrap. Is there a faster way to do this? This might be not good to know. I mean, I guess I don't know what I want to print here. Sorry, I'm just trying to print this here. I should probably add a space. That looks really ugly. Maybe we print it right here. Yo, some of these are really large. This doesn't help. Maybe I try and print it like this. What is the differentiator between a wall and a not wall? Should I just say the difference is 100 right now? So what I can do is I can say this is my end. This is my start. I don't think this is totally right. Does that look better? Oh, I need another one where I say there's one that's 0, right? Uh, happens if I set this to like... Well, I guess I know which one my... Yeah. So what if I, instead of doing 100 is greater than cur size? Does that change it? Or sorry, used avail. It'd actually be this way, huh? No. How do I calculate the walls is what I'm wondering. Maybe it is just somewhere around 100. Like this graph is definitely doable. Like you imagine a BFS where you're just fun. I don't think it's exactly like this, but I think this helps because the reality is your neighbor's function right here is I have this much disk available. Can I move any of my neighbors up, down, left, right to me? And if I can, then that's quote unquote a neighbor. And eventually I want to get it to like up over here in these spots. How do you finish this puzzle? It feels like there's two stages, right? One is get this up here, and then one is move it over. So maybe I print out the like what I'm wondering is, I probably also need the used avail total use size. What I'm just trying to discover is, can I just go straight across? Can you do this, by the way? No. So this is my end, and this is my beginning. So like I need to get this 70 to here. These are all in the 80s and 90s, and these are all in the 60s and 70s. How about row 2? Yeah, it is the same thing. Okay. Because I think we can do... Where was that? Like once we get it here, it's probably pretty easy to like swap it, move it around, swap it, move it around. Swap it, move it around. In fact, that you can calculate that number, right? It takes, if you start at this position, it's 1, and then 2, 3, 4, 5. To move it each time. Yeah, so I think we can count it. It's like imagine it's further away. All right, so like let's say it's right here. This is a terrible example because it's even smaller. But I can now swap it and then move this around. That's 5. So for each of these dots, it's like 1, 2, 3, 4, 5, whatever the number is. And then the last position will have me here and my underscore here. And then that's just 1 because now I'm done. I don't want to do the -1 error. Like we know this rotation is 5, right? 1, then 2, 3, 4, 5. And then you have to do 1 more to get there. So the distance between these two is like 0 and 2. It's 2 minus 1 times 5 plus 1, I think is what it is. So we can calculate it. Okay, so then the BFS we're doing is just what's the shortest path to get from here to here, and then we can calculate the rest. I think. Okay. So let's do a let dist to start neighbor equal BFS. We need the input. We need a point of x max x minus 1, like we want to go 1 before it, but our y stays the same. And we need our start point, which is like where the dot is. So we need to find that curve. So start is that. Let empty equal so we want to find it where the used is 0 and the so we map that to AV E dot unwrap. So this is like our empty spot. So we want to start at or sorry, let BFS full equal point x start dot x minus 1 y 0. So we're going to start at empty and go to BFS goal. So this BFS is just going to get our distance. I guess I don't need my start. I don't think I do. And so like, what is the answer? This to start neighbor plus like if it's 0 and 5, we know this is always 0, right? So it's just max x times 5 plus 1. But it wasn't quite that. The distance is 5, but I only need to do 4 of these rotations. Four of these like full rotations, because that will move me 4 away. So now I'm at position 1, and then I just have to slide it like that. And then we do our BFS. Okay. It's because this is an eye size. Okay. So how do we do our BFS? Let frontier equal vecdeck new frontier dot push back start 0, and then let visited fx hash set default visited insert start clone. Or actually, do I need to clone it? Because I think I. Of course, no, mute. So now we do while let some per dist equal frontier dot pump pop front if cur equals. I'm inclined to just do this. End return dist. Otherwise, we need to do our late neighbors function. My point is an eye size, so I can just do the mathish. So it's like let deltas equal I should probably do some of the math stuff here, right? I could just, do the mathy thingy. x equals cur dot x plus delta dot x, and y equals cur dot y plus delta dot y. So this is my next point. So I just, first of all, I just try and find it. So we don't find it, we just skip it because we know it's not a thing. If we've already visited it, ooh, I don't want to do that yet. I want to check to make sure I can move it first and then try and add it to my visited list. The thing that's got me here is like, do I need to track the sizes? The largest is 73. Oh, for the min available, I want to filter n dot total or n dot used equals 0. I think. No. I don't want this 0 one in here. Is that right? Okay. Yeah, I think I have to do like this thing where I say like um presumably my current is empty. So I just want to say if node dot used greater than cur dot available. Okay, so here's the problem I'm having is, doesn't that mean the grid has to be like mutable? And that means that the thing, I don't think I'm going to try to do it without. I think the assumption is there's just I definitely know I can move around the grid as long as I don't hit a wall. Like that's what I'm thinking. Where was that one? There was one that had a size of 64. So what does that even mean? Like I want to, I think what I have to do is like calculate the walls. So the question is like which one is a wall? Like which are the ones that I don't have to get into? But like see these first couple rows that I was printing. Well, what's this printing now? The second row. It Oh, it's not this, it's total. What okay. See, this is what I was expecting. Like it's saying like we can just create a wall. Um does this say something in the puzzle about this? In this example, most of the nodes are interchangeable. They're full enough that no other node data would fit, but small enough that their data could be moved. Yeah, like could be moved anywhere. So like what do you set that size to? Do we say anything that's 85 is a wall? Like in this example, I can definitely move this down here, this up here, this over here, and this over here. No problem. grid. So like the thing that I'm trying to figure out is here's my worry is like, do I have to track where my empty space now is? Okay, so like think about it this way. Like I can take this, I can take this and move it into it. Now I have 9 free. So I have 9 free now. I can move 6 and 8. I've already been here, no reason to move here. I think I'm gonna have to believe that this implies that I can move around anything that's like there's this weird gap right here, right? What does the top row look like? Oh, what is my used? Unavailable max used. The empty one. Available 85. Oh, that one is the smallest. So it is this value. This is what like determines whether it's a wall or not. I think. Yeah. Oops. So I just need to, like when I'm calculating my neighbors, I just say if node dot used is greater than start dot avail, continue. Oh, start is my point. Dang it. So let's do like wall size. Like we assume this is a wall. Okay. So we're going to go through all the deltas. This is taking me a long time to get here. We're going to go through all the deltas. We're going to say, we're going to check to make sure the next point is there. We're going to check to make sure it's okay. And then we want to check to make sure it's not been inserted or it's not visited. So if I think I dork up the clone thing all the time. Don't, I've learned before, don't delete random print lines because the first solution doesn't always work out. But let's just double check. Because we could probably almost do this one by hand. Because we have this. So we know we need to go 1, 2, 3, 4, 5, 6, 7, 12, 13, 16, 17, 18, 19, 20, 21, 22, 23, 24. I don't know, 40, 230 seems high, but I'm willing to try it. Let's just finish it. Please be it. Yeah, got it. Okay. That's not too bad. So, like, what were the sticking points for me? Kind of. Sometimes you have to like verify the puzzle input. I don't know. I suppose if you're just trying to do it competitively and do it fast, you kind of make assumptions that like, oh, the problem you're trying to solve is this. But I was really unsure about like, could I move things around? And just to be clear, like what would make that difficult is if I had to like track it. The grid changes at every state. So now I need to track the grid in the state, which is not like impossible to do, but it now means I have to track the whole grid. But I don't think you do. Like I think what like this was trying to allude to was as long as you weren't bigger than like, you know, this value, you weren't considered a wall, as it were. Right? So what is that saying? Like right here, this is like a not a wall. It's like this part right here is what it is, right? So Okay. Anything I could do to improve this? How long have we been going? Over an hour. You could definitely like definitely do that a lot. I don't think I need to parse it. I could impl add. That would probably help. Like that, because then I can do something like these ones become new. Is that the only place I really? Oh yeah, I use them right here. Haunt. Okay, that does make it look cleaner. You do the math a little bit easier. Um, do I actually use total here? Nope. I did trim today, but I didn't actually need it. I keep that reminder there so I know. So this is just AXB where criteria is met. And then this one is like that. And then this is it turns out to just be the size of the empty. Oops. Move the empty node is a little funny because you're not actually moving the node. Okay. I wanted to start trying commenting just so I remember what I did. We've done BFS a dozen times, right? So I think the only thing interesting here is our checks. Okay. How'd you do it? Anything different? Did I miss anything obvious? It definitely took me a little while to solve the part 2 compared to part 1. I think I got stuck mostly on, well, I had to figure out how to do it first, but then I did get stuck a little bit on what constitutes a wall. But I do think in the end I like the solution. I imagine this is the way you solve it, right? Is you have to BFS to get yourself here, and then you just have to realize that you can calculate that distance at the end. It's almost laid out to you in the instructions, right? Is the idea is you can move around. Like where it would have been, oh, and I did check this, right? Where it would have been tougher is if there were like walls in these 2 rows. So my problem doesn't solve it for the generalized solution then. Like if there were a wall right here, you then have to do like the mutations like down here and around. And in fact, there couldn't be both a wall here and here, because there's, once you put G over here, there'd be like no way for you to get this over to the other side. Like I think you need the actual box to do this rotation thing. You need like a 2x2 grid to properly do the rotate, and then to go around it, you need a 2x3, I guess, to go around it. So I mean, I think maybe I did luck out then, because I was actually going to say in a more generalized solution, like G can go this, like you could move G here or whatever, and then like say there was a wall here and here and here, but there was an opening path this way to right here. You could say like, okay, the next place that I need to move G is here. Now I need to do a BFS to move there. So that would be interesting to know if your other inputs did it differently. It wouldn't change the algorithm that much. You just say this is a wall, and now BFS from here to here or whatever, right? Because you know you can't use G to get there, so for most cases it would probably just be this, and you'd find it really quick. So within a depth of 5. So okay, I think I've talked enough about this. So thanks everybody. Hope you've had fun watching. Let me know what you did, and we'll talk to you next time. Bye everyone.